Alright, Chapter 4, Covalent Compounds. You want to start by looking over the objectives for the unit, the chapter. By the end of Chapter 4, you need to be able to do these 8 things. And so as you are working through your practice and finishing up your study modules, make sure that you can do these things, and that will help you prepare for the test. Alright, let's get started. Covalent bonds result from sharing electrons. If you remember back to when we talked about ionic compounds in the last chapter, there was a transfer of electrons, but with covalent compounds, we're sharing. The purpose of forming bonds for any element is to make sure that that particular element has a full octet. And so some elements, in particular nonmetals, will achieve this full octet by actually sharing electrons. So they give you an example here of hydrogen. Hydrogen gas is 2 hydrogen atoms bonded together with a covalent bond. And so by sharing a pair of electrons, each hydrogen was able to achieve a full octet. You should know that a covalent bond is a 2-electron bond. So the bond consists of 2 electrons. These 2 electrons come from the valence electrons. Those are the electrons on the outer shell. And it takes 2 electrons to make up a bond. Another vocabulary word that you should know is molecule. A molecule is this discrete group of atoms that's held together by a covalent bond. So when you hear the word molecule, generally we're talking about covalent compounds. Along with shared electrons in the bond, you have unshared electrons, and we call these lone pair electrons. Lone pair electrons. You might also see them referred to as non-bonding electrons. They are simply the valence electrons that are not involved in the bond. And so we can see with HF, H and F are held together by a covalent bond, but there are 3 sets of lone pair electrons around fluorine for a total of 8. So again, atoms share electrons to attain the electron configuration of the noble gas that is closest to that element. As we talked about earlier, noble gases are in group 18, and they have 8 valence electrons. And so they have achieved this full octet of electrons without forming any bonds. They are stable just by themselves. And so all the other elements are trying to look just like the noble gas by having that full octet. For hydrogen, a full octet is just 2 electrons, but for most all other elements, that would consist of 8. And that's why it's called an octet. The prefix OCT, oct, means 8. So covalent bonds are formed when nonmetals, 2 nonmetals, combine, or sometimes you have a metalloid that bonds with a nonmetal to form a covalent compound. So you might think, well, how many covalent bonds will a particular atom form? Excuse me. Hydrogen can only form 1 bond because it just has the 1 valence electron. But atoms that have 1, 2, or 3 valence electrons form that many bonds. Either 1 bond, if it has 1 valence electron. It has 2 valence electrons, it's able to form 2 bonds, or if it has 3, it's able to form 3. Some atoms have 4 or more valence electrons, 4 or more, and so they will form enough electrons to complete that octet. When we think about how And why is chemistry important? We can focus on our human body. Our body has chemical reactions going on all the time, and covalent compounds are important in our body. The picture here we see is of the heart and some blood vessels. It mentions several covalent compounds here. First and foremost is oxygen gas. We know that we have to breathe in oxygen gas so that it can be transported across our blood vessels and carried throughout our body. Our body is mainly water. Water is a covalent compound. Also, a couple of others associated with the heart. Nitroglycerin is a covalent compound that actually causes the blood vessels, or the muscles of the walls of the blood vessels, to increase the blood flow so that your heart can get more oxygen. You may have heard of nitroglycerin as a help in time when someone is having a heart attack. They can take a nitroglycerin tablet, and that just increases the flow of blood to the heart. And then there's another component called glycine. Glycine is the building block for protein that composes the muscles of the heart. So all of these are very important to our body and to the function of our bodies. And so it's good to know a little about covalent compounds. Our next focus here will be on what's called Lewis structures. Lewis structures. And so you can draw a Lewis structure of a single element, or you can draw Lewis structures of compounds. And so our focus will be on drawing Lewis structures for compounds. And notice that you see three examples here. These Lewis structures show how the valence electrons are arranged within the compound themselves. It tells us if they're bonded electrons or lone pair electrons. It also shows us what shape the molecule will take on. And so we see these three examples. The first one's methane. And so this would be the Lewis structure for methane. You'd use a single line for a single bond. And just remember that every line is worth 2 electrons. It takes 2 electrons to make a bond. And the goal of atoms forming the bonds is to fill the octet. So we see carbon is in the center of this molecule, and around carbon there are 4 bonds. And each of the 4 bonds has 2 electrons. So that's a total of 8 electrons for carbon in this molecule. So by joining up with these 4 hydrogen atoms, carbon has achieved a full octet. We can look a little further at the shape of the molecule, and we'll learn more about that in the future. The shape of the electron is shown here with this space-filling model, and this is called the tetrahedral shape. Tetrahedral shape. The next example here is ammonia. Ammonia is a common cleaning supply that you might be familiar with. NH3 is the formula. And the Lewis structure is shown here. And you see the arrow pointing to the 1 lone pair of electrons. So again, nitrogen is the central atom here, and it is surrounded by a total of 8 valence electrons, 3 bonded electrons, and 1 lone pair. And then we can see from the shape that because of this lone pair of electrons, the shape has changed slightly. Even the name has changed. So this is called trigonal planar. And again, more on this in later discussion. The last example here is water, and the Lewis structure for water is here. There are 2 lone pairs of electrons and 2 bonded hydrogens. And this shows the shape of water molecule, and this shape is called bent. It has a bent shape. So as I said earlier, you will need to be able to know how to draw these molecules. And so here are some general steps to follow for drawing Lewis structures. So the first thing you want to do is you want to be able to count all of the available valence electrons within the compound. Count the available valence electrons. And so to know how many valence electrons a particular element has, you would consult the periodic table. In fact, if you don't have your periodic table out, you should pause the video and find your periodic table. So we want to look at the group number of the element that we are trying to figure out how many valence electrons it has. And remember, the valence electrons are found in the ones place of the group number. Group numbers go from 1 to 18. And so you find each of the elements within the compound and you add up how many valence electrons you have available to actually draw this Lewis structure. The second step, once you've done that, is to connect each of the atoms to the central atom. You're going to connect them with a single bond to start with. And after you've done that, the third step then would be to place the remaining valence electrons around the outside atoms. And notice that they need to be placed in pairs. And so we'll see what this looks like in a moment. After you have placed all of the available valence electrons, the last step then would be to verify that every atom in the compound has a full octet. And again, most of the time that means 8, but for a few atoms there's less than 8. And even some atoms more than 8. We'll get to those exceptions. So let's take a look at a couple of practice problems for drawing Lewis structures, and we're just going to follow these steps. So again, the first step was to count the number of valence electrons. So our compound is here, CH3Cl, and again we're going to need our periodic table because it says for the main group elements the number of valence electrons is equal to the ones place of the group number. The ones place of the group number. Alright, so if you will find carbon on your periodic table, carbon is element number 6. We want to take a look at the group number. Carbon is in group 14, and so we take the ones place of 14, which is 4. Carbon has 4 valence electrons. And when we look in the formula, we see there's only 1 carbon, so 1 times 4 is 4. So carbon is going to contribute 4 electrons to the Lewis structure. The next element in line is hydrogen. There are 3 hydrogens, and I know that because there's a subscript of 3 that follows hydrogen. Finding hydrogen on the periodic table, we see that it's in group 1, and so it has 1 valence electron. 3 times 1 is 3. Next is chlorine. Chlorine, there's only 1 of those. And if we find chlorine on the table, it's in group 17, one of the halogens. Taking the ones place, there are 7 valence electrons in chlorine. 1 times 7 is 7. So now we simply just want to add these numbers together to get the total. And so that would be 14 valence electrons. CH3Cl has 14 valence electrons available to draw the Lewis structure. So once we've determined that, we want to connect all of our atoms to the central atom. And so we want to connect them with a single bond. The way to figure out which atom goes in the middle, if you will look at your formula, generally the atom that only has 1 element represented goes in the middle. Here we see carbon is 1 and chlorine only has 1. If carbon is in the compound, always put carbon in the middle. So we are going to put carbon in the center, and we're going to surround carbon with all of these other elements. So we have 3 H's, and then we have a chlorine, Cl. We're going to connect them all with a single bond. So just draw a solid line to represent the single bond. And each single bond represents 2 electrons. So when we count how many valence electrons we've used, we see there's 2, there's 4, there's 6, and there is 8. So far we've used 8. And remember, we had 14 available, so we still have some electrons to place. That is step 3. So we're going to place the remaining electrons on the outside atoms first. This is key. Put a star by this. Always go with the outside atoms first. Another thing to realize is that hydrogen, when it forms a bond with another element, that's all of the electrons it can hold. It cannot have any lone pairs of electrons next to hydrogen. So the only place we have for our lone pairs of electrons is the chlorine atom. And so we have, we are going to place the remaining electrons down in pairs. So with our counting our bonds, we have 2, 4, 6, 8. And then we're going to place 2 more dots, that's 10. 2 more makes 12, and 2 more makes a total of 14. 14 was our number that we counted at the very first step, and so we know that we have placed all of the available electrons. Okay, our very last step then would be to verify. We want to make sure that every atom is showing a full octet of electrons, and when we take a look at each of the individual atoms, we can count the electrons that are surrounding that atom and decide if it has a full octet. So let's look at this atom. If we take a look at the hydrogens, this particular hydrogen has a bond right here with carbon, and that bond is 2 electrons. And so hydrogen only needs 2 to be satisfied. So this hydrogen, and this hydrogen all have their full octet. And if we take a look at carbon, carbon is a central atom. So carbon has 2 electrons here, 2 electrons here, 2 electrons here, and 2 electrons here. So that's 2, 4, 6, 8. So we know that carbon has a full octet. Then lastly we take a look at chlorine. Chlorine is sharing the bond with carbon. So that's 2 electrons for chlorine. And then we have 2 more is 4, 6, 8, by counting those lone pairs. So again, chlorine has a full octet. So this particular Lewis structure is finished. This would be your final Lewis structure is here, and that's all there is. So the last step in the verify says verify that all the atoms have a full octet. If not, then you need to create a double bond. And so we'll take a look at an example where we have to make a double bond in just a second. Let's talk about multiple bonds. When you have one lone pair of electrons, sometimes you will take that one lone pair and you will convert it into a bonding pair. So a lone pair of electrons can be turned into a bonding pair if needed. And so that would create what's called a double bond. And so a double bond is when 2 sets of electrons bond. And so in this particular Lewis structure, this is oxygen gas, we see that oxygen is sharing 2 sets of electrons in the bond, one pair in each bond. We can also have a triple bond. So a triple bond is 3 2-electron bonds, and the triple bond is as high as you can go. There's no such thing as a quadruple bond. All right, so let's see what a double bond looks like. We're going to follow the same steps. Our molecule is here, C2H4. Our first order of business is to count the valence electrons. And again, you count the valence electrons by looking at the group number. Carbon is in group 14, and so it has 4 valence electrons. And in this particular compound, there are 2 carbons, so you have to multiply 2 by 4 to get 8. 2 times 4 is 8. Hydrogen only has 1 valence electron, but notice in the formula there are 4 hydrogen atoms, so 4 times 1 is 4. We add these together to get a total of 12. We have 12 valence electrons available to build this Lewis structure. Step 2 then would be to connect. We want to connect all of the atoms with a single bond. In this case, we do have carbon in the compound, but we have 2 carbons, so we don't really have a central atom. In fact, we're going to let both of the carbons act as a central place. And so we want to connect all of the letters with a single bond. So you put the 2 carbons in the middle, and then you just distribute the H's out evenly around the carbons. And so this is the best arrangement. Instead of having 3 carbons on one three hydrogens on one carbon and just one on the other, we kind of space them out evenly. So we did count, connect, and third step would be to place. And so when we connected our atoms with a bond, we used some of our electrons, our valence electrons. We have 2, 4, 6, 8, 10. So we're already accounting for 10 of the 12 valence electrons. So we only have 2 more electrons. And so we're going to place them right here on the carbon. Remember that lone pair electrons cannot be on the hydrogen. So you could have easily put the lone pair here instead of here, and that would be fine as well. But just know that they have to go on the carbon atom. All right, and then the last step, we want to look to make sure that all atoms have a full octet. So we're verifying that all atoms have a full octet. And when we look at this structure here, we see hydrogens are fine. When we look at this carbon, we see it has 2, 4, 6, 8. So that carbon is fine. But this first carbon, it only has 2, 4, 6. It does not have a full octet. So we need to create a double bond. And so we're going to take this lone pair of electrons and turn it into a bonding pair of electrons. And so the result then is a double bond. By using the double bond, we can see that both carbons have a full octet. Let me just count them with you. So this, if I start with this first carbon, it has 2, 4, 6, 8. And then if I go to the second carbon, it also is sharing the bond, so there's 2, 4, 6, 8. And so by creating that double bond, we see that everybody has a full octet. All right, so that's an example of multiple bonds. There are a few exceptions to the octet rule. Remember, octet means 8 valence electrons, and so most atoms generally follow the octet rule. Boron is a notable example. So boron, if you'll look at that on your periodic table, element number 5, it has 3 valence electrons, and it is a fairly small atom comparatively. So it only needs, oh, I'm sorry, I've skipped ahead. Let me just back up. Sorry about that. This first sentence is talking about hydrogen. So hydrogen is a notable example. Sorry about that. Because it only needs 2 electrons. So we've talked about hydrogen, the fact that you can only have one bond with hydrogen, and it can never have any lone pairs. Now to what I was saying about boron. Boron is another exception to the octet rule. Element number 5 is a fairly small element, only has 5 electrons total, and it is able to achieve the same stability with only 6 electrons. So when drawing Lewis structures, keep in mind that boron and hydrogen are exceptions to the octet rule. And then when we move to some of the bigger elements, elements that are found in the 3rd period and beyond, 3rd, 4th, 5th, 6th, 7th, these elements are larger and they have more orbitals available to them. And so in particular, the elements in the 3rd period have the d orbitals available. And these are empty orbitals. And so they can have a space to put some extra electrons. So some common examples that we see, phosphorus and sulfur, they can have more than 8 valence electrons. And so you can see how, if we take a look at this particular Lewis structure with phosphorus in the middle, and we count the valence electrons around it, so each bond has 2 electrons, so there's 2, 4, 6, 8, 10. So this phosphorus atom has 10 valence electrons around it, and the sulfur with its 2 double bonds, we can count there's 2, 4, 6, 8, 10, and 12. So since these atoms are on the 3rd row, and anything below the 3rd row, these elements can have more than 8 valence electrons. All right, our next topic is called resonance. Resonance, and when we start drawing Lewis structures for polyatomic ions, we have to take into consideration their charge. So remember that all ions have a charge, and as we're counting the valence electrons for that Lewis structure, if the charge is negative, you're going to add an extra electron to the total. And if the charge is a positive, then you would subtract an electron from the total. So let's think about the reason behind this. If we have an anion has a negative charge. And if you think about how did that anion get a negative charge, it's because there is one more electron than there is protons. And so since an electron has a negative charge, if I add an electron, the overall atom is going to take on a negative charge. On the other side, if I have a cation with a positive charge, that element became a cation because it lost one electron, or 2 or 3. And so by losing negative electrons, it takes an overall positive charge. So the example we see here is a polyatomic ion known as cyanide, Cn with a -1 charge. And so you can see that we are counting our valence electrons here to getting ready to draw the Lewis structure. And so we find carbon has 4 valence electrons, and there's one of those. Nitrogen has 5 valence electrons, and there's only one. But then you have this -1 charge, and so they've added in an extra electron for a total of 10. As you're drawing Lewis structures, when you count to the valence electrons, you should count to an even number. If you count the electrons and it's an odd number, then you should take a look and make sure there's not a charge. There are a few exceptions to this, but for the most part, you'll always have an even number of electrons. And so when we get ready to draw the structure of cyanide, once we've counted, we're going to place, and since there's only, we're going to connect. Since there's only 2 atoms, we would just connect the 2 atoms together with a single bond and then place the remaining electrons around. And when we do that, we see that neither carbon, or I guess just carbon, does not have a full octet. So we're taking away 2 lone pair of electrons from nitrogen and turning it into a bonding pair. And then we take away 2 more lone pairs around nitrogen and turn those into a bonding pair. So what we end up with is a triple bond between carbon and nitrogen. We verified that everybody has a full octet. And then the very last step, anytime your Lewis structure has a charge, you have to put a bracket around it. And you have to indicate the charge on the outside of that bracket. So just keep that in mind as well. There's something else we need to look at in terms of Lewis structures, resonance structures. So what is a resonance structure? Polyatomic ions typically take on Lewis resonance. So we need to see what that's all about. It says resonance structures are 2 or more Lewis structures having the same arrangement of atoms, but a different arrangement of electrons. And so here this bicarbonate ion is shown 2 Lewis structures are drawn. And so if we take a close look, we see that the only difference between these 2 structures is the location of the double bond. And so the double bond can go between this carbon and this hydrogen, and it could also go between this carbon and this hydrogen. And so simply changing the location of that double bond creates a different structure. And so we have to draw both structures. Notice it says that neither Lewis structure on its own is able to describe the arrangement of electrons, so you have to have both. You want to be careful about moving that double bond and what that does to the lone pair of electrons. The position of the lone pair is different, so you want to be careful about that. So these are the two resonance structures for the bicarbonate ion. And notice in the middle there is this arrow, a double-headed arrow. This is an indication that these two structures go together and that they are said to be in resonance with each other. So a true structure, the true structure for the bicarbonate ion is actually called a hybrid of the two resonance structures. So think about what hybrid means. You might have heard of a hybrid vehicle where it runs on gas sometimes, runs on electricity sometimes. So it kind of can go back and forth. A similar idea is here when we have resonance structures of molecules. So when a molecule is in resonance, this resonance stabilizes a molecule by spreading out the lone pairs and the electron pairs in the multiple bond, spreading these out over a larger region of space. And so a molecule or an ion that has two or more resonance structures is said to be resonance stabilized. And so resonance structures. Remember to put the double-headed arrow between resonance structures. We can look at another example here of ozone. Ozone is a molecule found in our atmosphere. It protects us from ultraviolet radiation from the sun. This is a very common element that shows resonance. And so when we compare the two structures here, we see that there is a different location of the double bond. And so we have to draw both structures and put the double arrow in between. Since ozone does not have a charge, you see there's no brackets around ozone, it's just the double arrow. So this would be an example of resonance structures of ozone. All right, we're going to pause here, and the remaining of the chapter will be taken up in a separate video.